Welcome back, everyone, to the Deep Dive. Ready to dive into something fascinating today?
Absolutely. Always up for a challenge.
All right, so today it's all about a pretty cool concept. It links the surface area of a sphere and a cylinder.
Sounds complex.
It is, but also super elegant thanks to Archimedes and his, get this, Hat Box Theorem.
Hat box theorem. Okay, I'm intrigued.
Right, so picture this. You have a sphere, like a perfectly round ball,
Got it.
and it fits snugly inside a cylinder, like one of those old-school hat boxes.
Oh, I see it now.
Archimedes figured out that their surface areas are, well, surprisingly related.
No way! That's amazing. Didn't he live like way back in ancient Greece?
Yeah, like over 2,000 years ago. And lucky for us, we have a lecture on this very theorem, audio and transcript, so we're really going deep today. But first, how do you even calculate a sphere's surface area? It's not a flat shape.
Right. It's all curved. That's where Archimedes' genius comes in. He didn't have fancy formulas back then, so he went geometric. Imagine that sphere inside its cylindrical container and boom, compared their areas.
So he's thinking visually, kind of like solving a 3D puzzle.
You got it. Now, follow me here. The cylinder's circumference, that's 2r, where r is our sphere's radius.
Okay, circumference, we're talking about the circle going around the sphere.
Exactly. And the cylinder's height, it's just the sphere's diameter, which is, you guessed it, 2r.
Gotcha, circumference and height. So the cylinder's basically like a wrap around the sphere.
Right. Now, multiply circumference times height, and you get the cylinder's lateral surface area. It's 4y. And wait for it, that's the sphere's surface area, too.
Hold on, seriously. Just from picturing them together, that's a major aha moment.
It is. This super simple formula shows us a deep connection between these shapes, like a hidden order in the universe. That's why Archimedes' work is so cool.
It's beautiful how a complex idea has this straightforward answer. But the lecture keeps going, right? It gets even more interesting.
Oh, yeah. Now imagine slicing that sphere and a cylinder combo with two planes. The cuts are perpendicular to the cylinder's axis. You basically create a band of both shapes.
Okay, like slicing a cake, but, geometrically.
Perfect analogy. And what Archimedes figured out is that even for these slices, his observation holds up. The sphere's curved surface area on that slice equals the area of the corresponding cylinder band.
So no matter how we cut it, the relationship stays true. How did he even prove that?
He used this brilliant idea of breaking down the surfaces into super tiny areas called area elements. Think of them like microscopic puzzle pieces making up the whole shape. Now, the lecture gets into the math here and uses cylindrical coordinates.
Now, if you're thinking cylindrical coordinates, well, imagine polar coordinates from high school. But in 3D, it's like giving directions on a spiral staircase using distances and angles.
Exactly. It's just another way to describe points in space. And using these coordinates, the lecture shows how the area elements, both on the sphere and the cylinder, they actually simplify to the same expression.
Whoa, so even at a super tiny level, those areas match up. Wild.
It is. And this is the key to the whole proof. It means that no matter where you slice the sphere and cylinder, as long as the cuts line up, the areas of those bands will always be equal. It's like every tiny patch on the sphere has a perfect match on the cylinder.
Mind blown. We've gone from visuals to thinking about these tiny matching areas. It's pretty amazing.
It is, and it gets even crazier. The lecture uses another coordinate system, too, called spherical coordinates. Think of them like latitude and longitude, but on a sphere. Guess what? These coordinates show that the matching area elements are actually, get this, congruent rectangles.
Wait, congruent rectangles on curved surfaces. Now that's hard to picture.
It is counterintuitive, but that's geometry for you. It turns out the size of these rectangles, they kind of swap lengths between the sphere and cylinder, but the area stays the same. It's like a visual representation of how these shapes are linked together.
So cool. So no matter how we slice it, literally, the surface area relationship between a sphere and its cylinder holds up. And we can even see it with these matching rectangles.
Exactly. The whole thing comes back to those area elements. By breaking things down and using different coordinates, we unlock a deeper understanding of the Hat Box Theorem.
This has been a wild ride. Visuals, tiny areas, coordinate systems, wow. But we're not done yet. There's still more to this Hat Box Theorem. Stay with us. We'll be right back to continue our exploration.
It's kind of mind-blowing, Archimedes figured all this out like 2,000 years ago. No computers, no fancy tools.
I know, right? Just pure brain power. Makes you appreciate his geometric approach even more.
For sure. And the lecture actually gets into some of the history, which makes it even cooler.
Oh, I love a good history lesson. Helps me understand the why behind the discovery.
So for Archimedes, this hat box theorem, it wasn't just some math puzzle. It was like proof of the beauty and harmony he saw in the world.
So more than just numbers and formulas, he was searching for a deeper meaning in the shapes themselves.
Exactly. He was so proud of this discovery that he wanted a picture of it, the sphere and the cylinder, on his tombstone.
Wow. Talk about a legacy. It's like saying, this theorem, this is my life's work.
And get this, the Romans, they actually honored his wish. They built him a tomb with that very figure on it.
Wow. So even centuries later, people were still amazed by this relationship between the shapes. What was it about this theorem that captivated people for so long?
I think it's this human desire to find order in the world. The hat box theorem gives us a peek into that order. It's like a secret code unlocking a deeper understanding of the universe.
Secret message hidden in plain sight. Speaking of uncovering secrets, what about those spherical coordinates you mentioned earlier? They sound like a whole different way of looking at the problem.
They are. Think latitude and longitude, but on a sphere. It gives us a fresh perspective on the whole hat box thing.
Okay, I'm hooked. How do these coordinates change our view of those matching area elements?
Well, when you describe both shapes using spherical coordinates, you find that the matching area elements are, get this, congruent rectangles.
Wait, congruent rectangles. On a sphere and a cylinder, my brain is struggling to picture that.
I know, right? It seems impossible, but that's the beauty of math. It reveals these crazy connections that, at first, seem to defy logic.
So how do we wrap our heads around these congruent rectangles on curved surfaces? Is there a way to visualize it without short-circuiting our brains?
Okay, so try this. Imagine taking a flat piece of paper and wrapping it around a cylinder. You get a rectangle, yeah? Now imagine doing the same thing with a sphere. It'll be kind of warped, but you can still think of it as having these rectangular patches.
Ah, okay, I'm starting to see it. Even though they're curved, we can still find these matching rectangular areas on both shapes.
Bingo! It's like two different puzzles, but with some identical pieces. Those identical pieces, those congruent rectangles, that's what makes the Hatbox theorem tick.
So cool. It's like a mosaic, right? All these tiny pieces coming together to create the bigger picture.
That's a perfect analogy, and like a mosaic, every tiny piece in the Hatbox theorem is crucial for the whole thing to work.
This has been a real mind bender. Visualizing shapes, breaking them down into tiny pieces, even exploring different coordinates. So much depth in one theorem.
It really shows the power of human curiosity. Archimedes, with his limited tools, discovered a profound truth that still fascinates us today.
I feel like we've only scratched the surface. There's got to be more to uncover about the Hatbox theorem.
Always more to discover. Maybe this has sparked your own curiosity to find other hidden connections in the world.
I'm already looking at everyday objects differently. This is what I love about these deep dives. It opens your eyes to the wonders right in front of you.
Absolutely. And while we've covered a lot, there's one more fascinating thing about the Hatbox theorem we need to talk about.
Oh, now I'm really curious. What else is there to uncover? Okay, we're back and ready to wrap up our Hatbox theorem deep dive. We've seen the shapes, broken them down, even gone back in time a bit. What else is there?
We've been talking about surface area this whole time, but this theorem, it also has a volume component.
Volume. So now we're going from the outside to the inside of the shapes.
Exactly. Remember how Archimedes was all about that sphere-cylinder connection? Well, turns out it applies to their volumes, too.
Okay, tell me more about this volume link. I'm curious.
The lecture says that a sphere's volume is actually 2/3 of the volume of the cylinder it fits in. So that sphere nestled inside, it takes up 2/3 of the space.
2/3. That's so specific. Is there a reason it's 2/3 and not, say, half?
It all goes back to that elegant geometry. The lecture doesn't go into the full volume proof, but it mentions you can prove it using similar stuff as the surface area proof, breaking things into tiny pieces and analyzing them.
So like those area elements again, but this time we're figuring out volume.
Exactly. We're thinking about tiny bits of volume instead of surface area. And by comparing those tiny bits between the sphere and cylinder, you get that 2/3 ratio.
Wow. So this one theorem shows us all these connections, surface area, volume. It makes you think, what other hidden connections are out there just waiting to be found?
Totally. Math is full of these cool surprises. And what's really neat is that these relationships in math often mirror a deeper order in the natural world.
That's what I love about math. It's
Mm.
not just formulas. It's like a language to help us understand how the universe works.
Yeah. Archimedes and his Hat-box theorem gave us a glimpse into that order. He showed us how different shapes are connected in unexpected ways. And that idea, that search for hidden connections, that's what drives scientific discovery even today.
This deep dive has been awesome. We started with surface area, then explored coordinate systems, learned some history, and even talked about volume. So much from one theorem.
It shows how much you can learn when you really dig into a topic. Like we peeled back the layers and found all this complexity and beauty underneath.
That's what the deep dive is all about, exploring a topic, finding connections, and really understanding the world around us.
And sometimes the coolest discoveries come from the simplest things, like the link between a sphere and a cylinder.
So true. The next time I see a ball or a can, I'm going to be thinking about all this hidden geometry.
Me too. And with that, we've reached the end of our deep dive into the Hat Box Theorem. Hope you enjoyed the journey.
Thanks for joining us. Until next time, keep those minds curious and stay tuned for more exciting deep dives.